Welcome you all for the structural analysis course. This is a week 6 lecture 2 CDT7 analysis of frame using moment distribution method. Right. So these are the lecture outcomes. So we'll see a symmetrical portal frame, how to analyze the symmetrical portal frame by using moment distribution method. I've considered a portal frame non-sway portal frame. So as I told you in the previous classes, so before going to analyze the frame, so you need to identify whether the frame is a sway frame or non-sway frame. So coming to this frame, this is a non-sway frame. How we are deciding this is a non-sway frame based on three categories. So three factors we need to consider for the deciding sway or non-sway. First one is type of support. So type of support. So if you observe, the supports A and D are the two supports. A and D are the two supports. They are fixed supports and they are at the same level. So with this first criteria, we can say this is a non-sway frame. Okay. So coming to the second criteria, geometry of the columns. That is the moment of inertia of the column. So if you see the moment of inertia of column, both the columns is same. Moment of inertia of both the columns is same. That means this will produce non-sway. Okay, coming to the third criteria is related to load. So coming to the load must be symmetrical about vertical axis. If you see the load is symmetrical about vertical axis. So if it is symmetrical about vertical axis, then we can conclude that this is a non-sway frame. So third criteria also satisfying this. So these three conditions are saying that this is a non-sway frame. Non-sway frame. This given frame is a non-sway frame. So non-sway analysis we have to, that means delta is equal to 0. That means sway will be equal to 0. Okay. So coming to AB span, A is a fixed support. AB span is subjected to uniform distributed load of 12 kN per meter. Similarly, CD span is also subjected to 12 kN per meter, and BC span is subjected to 2 point loads, 30 kN and 30 kN distance of 2 meters from the left and right supports, 2 meters from the left support as well as the right support. Okay, so this is symmetrical portal frame. Right, first of all, for the analysis of this frame, the first step where we need to calculate the fixed moments. Okay, in the step 1 we have to calculate fixed end moments. Yeah, so our given frame is a symmetrical portal frame. This frame is subjected to uniformly distributed load for the columns of intensity 12 kN per meter. This is a uniform distributed load, and this is also uniform distributed load for the AB. For AB column as well as CD column, the intensity is 12 kN per meter. And BC span is subjected to two concentrated point loads. 2 point loads, they are located 2 meters from the left and right supports. So this is also 2 meter. Okay, now coming to AB span, the beam is subjected to, fixed beam is subjected to uniform distributed load. We know the formula for the calculation of fixed moments. That is, MFAB will be equal, let us say this is A and this is B. MFAB will be equal to minus WL square by 12. MFBA is equal to plus WL square by 12. This will produce the clockwise effect. So here we have resisting moment will be clockwise. Here we have resisting moment at A is anti-clockwise, resisting moment at B will be clockwise in nature. Okay, if you substitute W is equal to 12 and L is equal to 4, you are going to get the fixed end moment. MAB is equal to minus 16 kilonewton meter. Okay, similarly MBA is also plus 16 kilonewton meter. Same formula, but the only thing is the sign will be different. Okay, coming to the BC span. So we'll see BC span later. Coming to CD span and DC span, they are similar to your AB as well as BA. So WL square by 12 will use. So minus 16 plus 16. Load is also same. So MFAB is equal to MFBA is equal to MFCD is equal to MFDC is equal to 16. But only difference is the sign. Okay, that you need to just carefully observe. Okay. So now coming to BC span. So BC span is subjected to a load of 30 kilonewton. 30 kilonewton per meter, 2 point loads of 30 kilonewton meter. So just think about it, students, how to calculate fixed moments. So we are not discussed about the for 2 point loads are acting on a beam, how to calculate fixed moment. Just think about it for a while, for just for 2 seconds or 3 seconds, 5 seconds. Fixed beam subjected to 2 concentrated point loads, 30 kilonewton as well as 30 kilonewton. So how to calculate fixed moments? Just think about it. The only thing what we need to do is first we have to remove the second load. First we need to remove the second load and apply first load and calculate fixed moment. We need to remove the second load. Sorry, second load remove and calculate fixed moment. So now in this case A will be 2 and B will be 4. So now we know if a eccentric point load is acting, then minus WAB square by L square. MFAB is equal to WAB square by L square. Let us say this is B and this is B. This is B and this is C in our problem, in our case. So MFBC is equal to minus WAB square by L square. MFCB will be equal to plus WAB A square B by L square. Okay. So now what we have to do? So first load effect is we are calculated. Coming to the second load effect. So first for that we have to remove the first load and we need to apply the second load on the beam. We need to apply second load on the beam and we have to calculate the fixed moment. Okay, we need to apply second load of 30 kilonewton 30 kilonewton. Okay, this is located 4 meters from the left support and 2 meters from the right support. So this is also minus W. A is equal to A, same formula, AB square by L square. But in this case, A is equal to 4, B is equal to 2. In this case, A is equal to 2, B is equal to 4. That you have to understand. Plus W, A square B by L square. So just substitute these values. For this first formula, A is equal to 2. For the second formula, A is equal to 4. For the first formula, B is equal to 4. Second formula, B is equal to 2. So you substitute these values. L is equal to 6 meters. To substitute, we're going to get MFBC as well as MFCB. So this is minus 40 and this will be plus 40 kilometer meter. Only thing you need to substitute. Okay. So after that, in the second step of moment distribution method of analysis, step 2, we have to calculate the distribution factors. So we need to calculate the distribution factors. So this is the distribution factor is depends upon its stiffness of member. Okay, we have to calculate the joint stiffness. First member stiffness we have to calculate. After the joint stiffness we have to calculate. After that we can able to calculate distribution factor will be equal to member stiffness by joint stiffness. That will be the formula for the calculation of distribution factor. So first of all, we have to calculate the member stiffness. So consider joint B and joint C. For the joint B and joint C, we have to calculate the distribution factors for the joint B as well as joint C. Okay. So write this tabular column. First column is joint, members, stiffness. Okay. Joint stiffness and distribution factor. So for the joint B, two members are meeting BA as well as BC. So BA as well as BC unit right here. For joint C, CD, CB as well as CD members are CB as well as CD members are meeting. So we know all the supports are fixed support. We know the stiffness of member K is equal to 4EI by L. 4EI by L. So substitute I value and L value in this equation. So for AB span I is equal to I. For BC span, for DC span I is equal to I. For only BC span 1.5 I. In case of BC span I is equal to 1.5. You substitute these values and calculate the member stiffness. So all are we are getting EI. So member stiffness KBA is equal to EI, KBC is equal to EI, KCD is equal to EI, KCB is equal to EI, KCD is also EI. So now we have to calculate the joint stiffness at the joint B. So for the joint B, two members are meeting, BA as well as BC. So stiffness of BA plus stiffness of BC will be your joint stiffness. So KBA plus KBC, if you add, that is your joint stiffness. So EI plus EI, 2 EI is the joint stiffness. Okay, coming to joint C, EI plus EI, you need to add summation of the member stiffness. KCB plus KCB. Add here. KCB is equal to EI, KCD is equal to EI. So that is your 2A, there is a joint stiffness. Now we need to calculate the distribution factor for this member. BA will be equal to stiffness of member by joint stiffness. Stiffness of member is EI. For BA member, stiffness of member is EI. Joint stiffness is 2EI. Just EI by 2EI. That means 1 by 2. EI gets cancelled. 1 by 2 is nothing but 0.5. So similarly for BC member, EI by 2EI 0.5. EI by 2EI 0.5. EI by 2EI 0.5. So this is case. In this case, this problem all are same because it's symmetrical. Loading is symmetrical. Geometry is also symmetrical about y-axis. So that's why all these distribution factors is same. So this distribution factors we are calculated. So after calculation of distribution factors, we need to draw the moment distribution table. Okay. So in the moment distribution table, we need to draw. So this is the moment distribution table. In this moment distribution table, first of all, we need to write the joints A, B, C, D. Okay. This is A, B, and it is C, and it is D. After that, we have to write at joint B, at joint C. We have distribution factors. Just now we are calculated. So distribution factor of BA is 0.5, distribution factor of BC is 0.5. Those we are written here. So after that, we have to write the fixed moments that we are calculating in the first step. MFAB is equal to minus 16, MFBA is equal to plus 16, MFBC is equal to minus 40, MFCB is equal to plus 40, MFCD is equal to minus 16, MFDC DC is equal to plus 16. That we need to write. So first step, we have to write joints. After that, distribution factors we have to write. After that, we need to write the fixed end moments. Okay, whether it is a beam or frame, thinking of support on either node, first of all, we have to write these steps. So first joint, distribution factor, fixed moments we need to write. So after that, we have to identify the joints, whether they are satisfying joint equilibrium equation or not, that we need to identify. So we have, these are the fixed moments, plus 16 minus 40. If you see joint B, it is not satisfying joint equilibrium, it is not following the joint equilibrium equation. That means summation of moments at joint B must be equal to 0. That is a joint equilibrium equation. So it is not satisfying. It is not equal to 0. That means plus 16 minus 40 is not equal to 0. So that there is some unbalanced moment is there. So we have to calculate that unbalanced moment by adding these two. So minus 40 plus 16, and that is minus 24 kilonewton meter is an unbalanced moment. Okay, minus to balancing it. So unbalanced moment is minus 24. To balance it, we have to add plus 24 kilonewton meter at joint B. So that means plus 24 we have to add it at joint B. To balance it, we need to add plus 24 kilonewton meter at a joint B. Okay. So why we are adding plus 24? It is not satisfying joint equilibrium equation. The summation of moments at joint B is not equal to 0. So that's why we are adding. So to satisfy the joint equilibrium equation, we have to add plus 24. We need to balance it. So right. So plus 24 we are adding here, plus 24 kilonewton meter we are adding here. Because of application of moment of plus 24, that is a clockwise moment of plus 24 we are adding. So because of application of plus 24 at joint B, it will distribute to its members. So at joint B we have BA member as well as BC member. So it will transfer to BA, that is 24 multiplied with the distribution factor of BA. So 24 multiplied with the distribution factor of BA is 0.5. So 25 by 1 by 2 is nothing but 12 kilonewton meter. So 24 minus 0.5, 12 kilometers. So that we have to add. So right, similarly for this span also, this is, to calculate unbalanced moment is plus 24. To balance it, we have to add minus 24. So minus 24 multiplied by 0.5 unit right here. Minus 24 multiplied by 0.5 unit right here. So after that, this is called balancing. So this stage is called balancing. So after completion of balancing, we have to, according to carryover theorem, we have to move half of the moment. We need to carry the half of the moment to the forward. Half of the moment to the forward. If the forward is fixed, then only we have to forward. That means carry half of the moment if the forward is fixed. So we are applying a moment of plus 12 kilonewton for the BA member. Because of the application, half of the moment is carried to support A. So that is 12 by 2, that is plus 6 kilonewton meter is transferred to A meter. So this is called carryover. So this 12 kilonewton is carried to the C support, minus 12 carried to the B support. Okay, minus 12 is carried to the D support. So this is carryover. So with this first cycle is completed. First cycle is completed here. Now if you observe at joint B, MFE, that means moment BA member is 0, moment for the BC member is minus 6, moment for the CB member is plus 6, moment for CD member is 0, moment for DC member is plus 6. So again we have to check the joint equilibrium equation in the step 2. Again we have to check the joint equilibrium equation for the step 2, cycle 2. Okay, this is your cycle. Okay, so for the cycle 2 also we need to check joint equilibrium equation. Okay, so it be 0 minus 6. So there is an unbalanced movement of minus 6 kilonewton meter is there. Unbalanced movement of minus 6 kilonewton meter is there. So for balancing it, we have to add plus 6, minus 6 unbalanced movement ఉందండి, దీన్ని balance చేయాలంటే plus 6 add చేయాలి, then it will satisfy the joint equilibrium equation. Okay, so if you add plus 6 kilonewton meter at joint B, that is a clockwise movement of plus 6, if you add at joint B, half of the moment is carried to BA member. According to distribution factor of BA is 0.5, distribution factor of BC is 0.5. So 6 multiplied by 0.5, that means BA is equal to 3 kilonewton, BC is equal to 3. ఎట్లా వచ్చింది ఇది? 6 multiplied with the distribution factor. 6 multiplied with the distribution factor. Okay, this is your balancing. Similarly for this also, we need to calculate the unbalanced moment of unbalanced moment. Unbalanced moment is plus 6. To balance it, minus 6 we have to add 0. Okay, so plus 6 ఉందండి, minus 6 add చేస్తున్నాం. So we are applying minus 6, that means anti-clockwise movement of minus 6 kilonewton meter we are applying at a joint C. Okay, so because of application, it will carry to the CB member, the moment will carry to the CB member as well as CD member. So how much it will carry? It's based on its distribution factor. Minus 6 multiplied with 0.5, that is your moment carried to CB member. Minus 6 multiplied with 0.5, that is moment carried to the CD member. So after calculation of balancing, so this is called a balancing technique. After that, half of the moment, according to carryover theorem, half of the moment we need to carry to the foreign. So half of the moment we need to carry to the foreign. This half we need to carry to foreign. This half we need to carry to foreign. This half we need to carry to the foreign. So similarly, again, so now here we have a joint with 0 minus 1.5, 1.5, 0. There is again one unbalanced moment is there. So to balancing it, so we have to balance it. So balance unbalanced moment calculate చేయండి, తర్వాత distribute చేయండి, carry చేయండి. So this is the procedure, continuous procedure we need to follow for the calculation of final end moment. Okay, so after calculation of this, you need to add all the moments. You need to add all the moments, then you are going to get the final end moment. Okay, final. Right, so after completion of this continuous process, so if you observe, the left side movement must be equal to right side movement. So the left side movement equal to right side movement, that we need to observe, and we have to add all the movements. We need to add all the movements. So to accuracy purpose, moment left side should be equal to right side. Accuracy purpose, we need to increase the number of cycles. Okay, so the thing is, the steps we need to follow: balancing, carryover. Balancing, carryover. This procedure we need to follow. After that, we need to add all the moments at C, all the moments at D, all the moments at C, as well all the moments at B we need to add, and you will going to get the final end moment. So these are your final end moments. Okay, we are getting the final end moments. So after that, we need to draw the bending moment diagram based on these final end moments. So for that, so first we need to draw the total frame as it is. So I'm writing here. So this is our total frame. I'll draw here. So moment at A, we have 8.02 kilonewton meter. So just now 8 point. So this is 8.02 kilonewton meter. That we need to locate. Okay, 8.02. This is 8.02 ordinate. At B, we have 31.99. So that ordinate is also we have to look at. So 31 is something more than 8 points. So the 31.99 ordinate we need to look at. This is 8.02 ordinate. After that, here also 31.99 ordinate we need to look at. Here also 31.99 ordinate we need to look at. Okay. Here also 31.99 ordinate we need to look at. Because moment at C will be 39. Okay. So moment at D is 8.02. That ordinate also we need to look at. So now what we have to do, just by using straight line, we join all these points. Okay, this point. Okay, this point and this point. Okay. So like that we need to add. So I'll erase and I'll draw once again. So we have to add all, we need to draw, we need to connect all these lines. Okay. Just okay. This is your hogging bending moment diagram. I'm drawing first hogging bending moment diagram. Okay. This is your hogging bending moment diagram. So this is your hogging bending. So this is due to fixed answer. Now we have to draw the sagging bending moment or applied bending moment diagram. So that for that, okay, applied bending moment. So here we have for AB span of uniform distributed load of 30 kilonewton, 12 kilonewton per meter is acting. So that we need to calculate the maximum bending moment. So formula for the calculation of maximum bending moment simply being subjected to uniform distributed load is WL squared by 8. So in this case, W is equal to 12 and L is equal to 4 whole square by 8. You will be able to get this is 24 kilonewton meter. This is the positive moment, that's sagging moment. Now we know for simplest about beam, extreme end moment is 0. At C we have plus 24, that means 31 here. So we know the variation of bending moment if the uniform distributed load is acting, the variation is parabolic variation. The parabolic variation with the parabolic variation, if you draw, so that is your applied bending moment diagram, applied bending moment diagram. So this is your applied bending. This is parabola and this is rectangle. Okay. Now after that, so coming to BC span. So BC span is different. So this also same for CD span is symmetrical. So bending moment is also same. We can draw as this AB span ki DC span ki bending moment and same. So this is also parabolic relation. So coming to BC span, horizontal beam. ఇక్కడ మనం ఏం చేయాలంటే we have to calculate the bending moment at various locations. Let us say this under the load we have to calculate the bending moment. So for this I am taking a beam of, for this I am taking a beam. Okay, beam is subjected to simply separate beam is subjected to 2-point loads. So we have to calculate the reactions first. So this is 30 kilonewton and this is also 30 kilonewton. So this is 2 meter and this is 2 meter and this is 2 meter. We have to calculate the reaction. So this is symmetrical load. RA is equal to 30, RB is also 30. So now we have to calculate the bending moment at this point. So we know the bending moment is 0 and the bending moment is 0. So because this is a simplest outward beam, we have to consider like that. Okay. So we need to calculate the bending moment at this point. Let us say this is A, this is A dash, B dash, B. At A dash and B dash we have to calculate. How to calculate a bending moment at A dash? A dash will be equal to this reaction multiplied with length. So 30 into 2, that is 60 kilonewton meter. Okay. So here we need to look at the ordinate 0. This is 60. Again, we have to calculate the bending moment for this side. Okay. That means we have to take 30 into 2. minus 60. So 30 into 2 is a 60. 30 into 2 is a 60 that we have to locate this ordinate. At B, we know the bending moment is 0. So that 0 ordinate. I'll locate here. So 60 ordinate will be here. At under the load 60. The load దగ్గర 60 ఉందండి. Just join these 2 points. That is your variation of bending moment. Now if you see, this is your net negative bending moment. This is your net positive bending moment. This is net negative bending moment. This is your net positive, net positive, net negative, net negative. So that values we will consider for the design of this particular elements or members. Okay. So this is the bending moment. So we'll see if column is subject, column is here we have column is subjected to uniform distributed load. ఒకవేళ కాలం మీద లోడ్ లేదనుకోండి, ఇంత కాలం మీద లోడ్ లేకపోతే ఎట్లా అవుతుంది బెండింగ్ మూమెంట్ వేరియేషన్ ఏ విధంగా ఉంటుందో విల్ సీ హియర్. కాలం మీద లోడ్ లేకుంటే the bending moment variation will be something like this. So bending moment variation is, so this is your bending moment variation if the column is subjected. కాలం మీద లోడ్ లేకపోతే ఇది bending moment variation. మిగతా the same ఉంటుంది బట్ ఓన్లీ bending moment variation అని కాలం పైన లోడ్ సేమ్ సపోర్ట్స్ is also same but కాలం మీద యూనిఫామ్ డిస్ట్రిబ్యూటెడ్ లోడ్ లేదనుకోండి. సో దిస్ ఈస్ ది వేరియేషన్. సో ఐల్ డ్రా హియర్ ఆల్సో. ఇక్కడ డ్రా చేస్తున్నాను క్లారిటీ ఉంటుంది. ఇఫ్ యు అస్యూమ్ ఆ లోడ్ లేదనుకున్నాం, కాలం మీద లోడ్ లేదనుకుంటే బెండింగ్ మూమెంట్ డయాగ్రామ్ వేరియేషన్ ఎట్లా ఉంటుంది అంటే, సో దిస్ ఇస్ ది వేరియేషన్. Is the ordinate 8.2 we need to locate. Here we have 31.9. Just to join these 2 points for straight line. Join these 2 points for straight line. And we have as this. Here the bending moment is as this. So this is negative and this is positive. This is negative and this will be positive. Okay. That is your bending moment diagram. If one of the support is hinged support in అనుకోండి, variation ఎట్లుంటది, bending moment variation ఎట్లుంటది. This is the variation. So this you need to observe carefully. Okay. For this you refer Ramanujam textbook for the calculation of bending moment, for the drawing of bending moment diagrams. Okay, that screen in this book is clearly mentioned. You go through that book. Okay, thank you, Vanilla.